All right. Hi, everyone. Thank you so much for joining our webinar today on 10BASE-T1S. We greatly appreciate your attendance and continued support for our company. Our host today is Juan Nava, and he is a senior field engineer here at Intrepid. If anyone has any questions throughout the presentation, feel free to use the Q&A feature or the chat, and we'll try to answer as many of them as we can before we finish. This webinar is being recorded, and we'll be posting the video on our socials as well as sharing the presentation slides. So make sure you're following Intrepid on all of our accounts so you can access those resources. Thank you all again, and without further ado, here is Juan.
Thank you, Jordan. Appreciate the introduction. Well, good afternoon. So we're going to be covering 10BASE-T1S. I can't give, in good conscience, I can't give this training without giving you some level of automotive Ethernet training. Not everybody understands that 10BASE-T1S is Ethernet. So if you never worked with Ethernet, I'm going to try and give you a really quick crash course on what it is. Otherwise, I would probably recommend you take one of our trainings that focuses more on that. If you would like to connect, there's my LinkedIn account. I would love to connect. And with that, we'll get started. So some of the things I'll be covering this afternoon is I'm going to talk a little bit about our company, just in case you've never heard of us. Like I said, we're going to cover a real brief version of Ethernet basics. We're going to go into the sort of the why 10BASE-T1S kind of exists. We'll deep dive 10BASE-T1S so you understand how it functionally works, because it is so different in other architectures. We'll cover a brief portion of zonal architecture. Specifically, what I want to kind of touch on is the challenges you'll probably face as you go through this. The other thing I'll touch on or cover is our tooling for 10BASE-T1S. So we do have a couple of offerings that we have, and then I'll do a show and tell. Normally, my class that I normally teach, we do a hands-on, but because we're remote, we got to do the show and tell. I will cover burst mode, which normally I don't cover in my normal class. I thought I'd throw in something new, and we'll go off that. If you have any questions, please post them on chat, as Jordan mentioned, and then we'll get started. So we are Intrepid Control Systems. We have been in business for a little bit over 30 years now. Well, actually, I think it's 30 years this month. We focus specifically on automotive network or in-vehicle network tools. Our companies or the headquarters actually focused in, or it's I swear I know how to say this stuff, but today it's just not going. Okay, let me focus. Okay, so our headquarters actually is in Troy, Michigan. So if you've been fortunate enough to take one of our classes, usually you can see through the glass windows the tools being manufactured. So depending where you're in the world, it all comes from Troy, Michigan. We do have a couple of offices around the world, so we can offer good service across all our customers. So we do have an office like in California. We have one in the UK, another one in Germany. We have a couple in China, Japan, and India. We also have a couple of distributors. And so, here we are. So to begin, we're going to cover a little bit about some Ethernet basics. And I want to start off with nomenclature. The reason I started off with nomenclature is that at least once a week I get a call, asking how do I connect my Fire 2, for example, into a automotive Ethernet network. And I just want you to understand that Ethernet may be Ethernet, at least at the naming convention, but you do need to understand some of the naming conventions to know what you're kind of talking about, because there are different versions. It's kind of like talking, if it's CAN versus LIN. So naming convention, the way Ethernet works is that you'll get a number, you'll get followed by a base, and then a dash, and some lettering, and possibly some numbers. And that tells you a lot. So the number actually tells you the speed of the connection. So we see like 1,000 base. We see 1,000 means 1,000 megabits, or also known as 1 gigabit. Base is just short for baseband. So whenever you see that, you're usually talking about Ethernet. Then you see a dash, and then the T tells you physically how it connects. So when you see a T in this case, it's 4 twisted pairs. So we go to the next one here, we see 100 base TX. 100 means it's 100 base, it's 100 megabits per second. Ethernet again, and TX. This happens to be 2 twisted pairs, as opposed to 4 twisted pairs. So the 1,000 base T is what you would see in your computer. If you see 100 base TX, for example, that's usually used for diagnostics, for specifically do IP, diagnostics over IP, which vehicles support nowadays, usually through the DLC, through the ALBO connector under the dash. when we look at the newer nomenclature, you'll see a G between the number and the base. And 2.5G would be something that is 2 gigabits, and it's T1. Now, T1 is one twisted pair as opposed to multiple twisted pairs, and that actually makes it automotive Ethernet. So the newer one now that came along, the one that's, everybody's kind of interested in, is 10BASE-T1S. So 10, it means 10 megabits. Base, again, same thing. T1S is T1 is for one twisted pair, automotive Ethernet, and then S stands for short. There's another version being developed that's T1L, which is long, and that was meant more for commercial application, which is a 1 kilometer long, where this one is 25 meters long. There's a couple different types of transmissions. So we have the first one, which is simplex. Simplex is a one-way street or one-way type of communication. So a PA system would sort of be one of those that it's one way. SENT, S-E-N-T, I can't remember what it stands for, but it's another form of communication that's used in engines for, it's a one-way communication. As soon as the device is powered on, it communicates one way. Then we have things that are half duplex systems or half duplex communications. Those are bidirectional communications. Usually that applies to like CAN and LIN. It also happens to apply to 10BASE-T1S. And half duplex just means one module at a time can talk. You also have systems that are full duplex, which means two devices can simultaneously talk on the same line. So when we talk about automotive Ethernet, even though you have one twisted pair, two modules can talk simultaneously on that line. So these are just different properties of Ethernet. So if you were to just kind of deep dive a little bit more into like 1000BASE-T1, for example, it's 4 twisted pairs, full duplex. Though technically this is not full duplex. What it is actually 2 twisted pairs that are transmit, 2 twisted pairs that are receive. But we normally see that as being full duplex. It uses this encoding, which is PAM5, which means it stands for pulse amplitude modulation. And it uses 5 discrete states. When you see these things like PAM3, PAM3, PAM5, and PAM4, for example, what that really means to you is that there's more than one bit that goes out on the bus. So it's supposed to, like CAN and LIN, where only one bit goes out at a time. 10BASE-T1S is also 1 bit at a time. It uses a differential interest recording. We'll talk about this a little bit more. And you have like 100BASE-TX, for example, is 2 twisted pairs. One's a receive, one's a transmit. And when we talk about like T1, for example, full duplex, but that's 1 twisted pair. Generally, Ethernet is described as 7 layers. Here are the 7 layers. The first layer being physical, second layer being data link, next one is network, and we have a couple more. Today, we're just kind of really more on layer 1 and layer 2. I'll talk a little bit about layer 3, but mostly we're going to be focusing on layer 1 and layer 2. Layer 1 is physical. So if we're ever talking about Ethernet, generally the ones that I talk about mostly with people is layers 1, 2, and 3. That doesn't mean the other layers are not important, but generally when we're talking, we're going to focus a lot more on those layers. Layer 1 is your physical. Layer 1 happens to be your connections, your wiring, the actual communication that happens on the bus, the microcontroller that's on the nodes or the ECUs to be able to communicate with us. And physical layer really applies to any version of Ethernet, whether we're talking 10BASE-T1S, 1000BASE-T1, or multi-gig T1, for example. Data link, which is the second layer, is where your MAC address resides. So most of you probably have looked at MAC address. MAC address stands for Media Access Control address. And it's basically a unique address that's given to your devices. So like your phone has one, your PC has one. Basically, anything that communicates over the internet will have an IP address, or I'm sorry, a unique MAC address. And it's just the address for the unique device. They also, layer 2 also supports VLANs. VLANs are a virtual local area network. And VLANs are used to kind of help you guide traffic also into specific areas. So certain lines or communication or certain networks or certain pieces of a network could be designated to be like VLAN 1, VLAN 2, VLAN 3. Sometimes they're given to specific areas. So maybe infotainment might use a specific VLAN number. Network layer 3, your network. This is really where your IP address resides. So it could be IPv4 or the newer version of IPv6. So physical layer, going a little bit deeper, there's It is depending on what version of Ethernet you're talking about, there's different physical connections. So we're talking about like 100 base T1 or 10 base T1S. A simple untwisted, a unshielded twisted pair is sufficient. So much like you see here in the picture, that's a unshielded twisted pair. Something that you normally see with CAN. So if you work with CAN, this is normally what you see. So anything that's 100 megabits or lower just needs a twisted pair. When you get to 1 gig or 1 gigabit or 1000 base T1, for example, shielding is optional. What I've seen is that it really depends on the environment that it's in. So if it's an environment that's kind of noisy, maybe there's a lot of power lines around it, there's maybe other communication lines, it might require shielding, but it may not. So it just depends kind of on the location where it's in the vehicle. When it comes to anything that's multi-gig, so 2.5 gig, 5 gig, 10 gig, the shielding is required. There's no optional for that. And so general Ethernet is 15 meters long. However, the 10BASE-T1S is 25. Now, when we talk about Ethernet, and this doesn't apply necessarily to 10BASE-T1S, but Ethernet is actually a point-to-point network. What that means is that there's always going to be one module connected to another module. So network usually Ethernet uses switches to communicate between different modules. You don't necessarily need a switch if you only have two modules. So vehicles, that are a little bit on the older side, they don't usually use switches. They, like for the infotainment, there's just usually a connection between a module and maybe like the display, for example. So those don't need a switch because they're just communicating directly. But when we look at networks that are a little bit more complex, where you're using a lot more than two modules, you need a switch in order to be able to allow them to communicate. So this is sort of the gateway. It's technically not a gateway, but if you're not used to Ethernet, switch is sort of the gateway between one module to another. If you notice from this picture here, every module has a connection, a line that directly connects to a switch. And I just realized that is misspelled. So every network or every device has an individual connection. So if I wanted to add an ECU, another ECU here, or ECU or node 6, for example, here, I wouldn't be able to add these to the switch because I would need another physical connection in order to add that. So those are point-to-point, and they are directly connected, at least for the non-10BASE-T1S versions. So when it comes to the MII stands for Media Independent Interface. This is something that's found pretty much it should be found in everything that you're dealing with Ethernet. And the MII actually exists at layer 2. Layer 2 happens to be where the actual Ethernet frame is formed before it gets transmitted over the bus. So this part is generic. So regardless of what Ethernet version you're talking about, whether we're talking about 10BASE-T1S, 1000BASE-T, this layer is the same. The layer 2 or the MAC layer 2 is the same. What changes physically is layer 1. So if I have a version of Ethernet here that's 100 base T1, for example, and I need to update it to be 1000 base T1, I don't have to redesign the module. All I have to do is really just change this one layer, and now it supports the new version of network or the new version of Ethernet. So same thing, I could take this 1000 base T1 and change it over to 10 base T1S, and now I have something that supports that new version of Ethernet. So this is, again, a common piece. So this is sort of what makes some of these switches capable, especially as we go forward into like software-defined vehicles or zonal architectures, is that these switches can support multiple versions of Ethernet. And internally, once they get to layer 2, it just sort of passes the data over to the new channel. So, when we talk about incompatibilities, I forgot to mention early on when we talk about the different versions of Ethernet, like 100 base TX or 1000 base TX is compatible with like 1000 base T. That's the only one that's compatible. All the other ones are not compatible with each other. You do need the proper tool. So if you're working with 100 base T1, just because your device says Ethernet, it doesn't mean it supports it. You actually got to get the right tool that supports specifically the version of Ethernet that you have. So we have things like media converters. Media converters allow you to convert from one type of Ethernet over to a different one. So for example, a RAD-2, or sorry, a Moon2 can be either 100 or 1000 base T1 on the module side, and then on the computer side, we would either connect through 100 or 1000 base T. This allows it to convert the the four pairs into the single twisted pair. So because they talk differently, this allows us to kind of use this. We also have a Moon 1 that does 100 base T1 to a 100 base T or TX, but the Moon 2 will do two different versions. Now, devices that have more than one capability, meaning they can do more than one speed, they're not dynamic. So you kind of set it, and then you do your testing. You can, however, go back to the device and reconfigure it and do, move it to a different module, maybe supports a different speed, and be able to connect it. It's not meant to be dynamic to where it switches between these speeds. It's meant to be set to one, and you test to that module. Moon 3 does the same thing. It just happens to do it at the multi-gig level. So this one supports 2.5 gig, 5 gig, and 10 gig Ethernets. So these are becoming quite popular nowadays. 10BASE-T1S is being adopted fairly quickly, and also these multi-gigs are also adopted. Like I said, all these things. So layer 2 is where your MAC address resides, but it also happens to be where the Ethernet frame gets formed. One thing I didn't have a slide for is that generally we have all these different layers, and they're all encapsulated pieces. So layer 7 will encapsulate its data. It will put its data together, it put a header part of it, and then encapsulates it, and then moves it down to layer 6. Layer 6 does its own thing. It adds its own piece, encapsulates what it got from layer 7, puts its own data, encapsulates it, moves it down the stack. So once you get down to the stack, layer 2 is really where the full Ethernet frame is formed, and then all it has to get past to layer 1 to actually, send it on the wire. So Ethernet is a little bit different than from like CAN and LIN. So LIN can support up to 8 bytes of data. CAN can do up between 0 and 8 bytes of data. CAN-FD can do between 0 and 64 bytes of data. However, Ethernet can support between 46 and 1500 bytes, or 1500 bytes. Now, one thing to understand is that if we wanted to send, let's say, 2 bytes of data, you still would have to pad the rest of the frame or the rest of the message to be able to do the minimum 46 bytes. One thing to understand also, that even though we're saying 1500 bytes of data here, the reality is that what actually gets sent out on the bus is actually a little bit lower than 1500, because there's other things that get added by the different layers that would take up space. So even though we might send 1500 bytes of data, actual useful data or the data that's being transferred will be less than that. How much really depends on what the other layers are adding. I won't bore you with the rest of the details here for the other pieces of the frame. If you want to learn more about this, I recommend you take our automotive Ethernet. We'll go each, byte by byte or bytes by byte, depending on what section, and then we cover that. For today's, I'm trying to keep it simple, so hopefully hold your attention for approximately 90 minutes. There's network and addressing methods. There's 3 different kinds. So the first one is unicast. So let me stop there for a moment and kind of go back. So when we talk about LIN and CAN or CAN-FD, for example, those are broadcast messages, meaning that if there's more than one module on the bus, all the modules that are on that bus will see a message that gets transmitted. Now, whether they consume it or not, that's a different question, but they will see the message. So unicast is what Ethernet allows you to do is with switches, you can kind of determine who gets that data. Unicast is a way to just communicate between one module and another one. However, it will go through the switch. The switch determines based on the MAC address, depending on this kind of switch, you might use the IP address to determine where it's going to go. So if ECU 0 wants to communicate with ECU 1, it would use the MAC address specifically to this ECU 1 just to talk to it. So it's like equivalent to you and I walking out the room and just talking in private. It'd just be you and I. The other option that we have is multicast. So multicast is when you want to communicate one module to several modules, though not all. So we would want to limit it. So, we could limit to just maybe a group. So let's say we want to go to lunch. I would do multicast, meaning I would probably just ask a few people to go to lunch because my car can only fit so many people, and then we can go to lunch, right? So it's just, that would be a sort of multicast, meaning we're only keeping it to a subset. Just it could be 2 modules, it could be 3 modules, it could be more. And then we have the final one, which is broadcast, which basically means everything. So technically, we look at what we're doing right now, that would be more of a multicast, because we're doing a subset of everybody that could potentially use this training, right? There could be more. If we're communicating to the entire world, then it would be a broadcast. I don't know if that maybe helps or makes it worse. But broadcast would communicate to all the modules. And if any of these modules are switches, because you can have more than one switch in a system, there's other modules that would broadcast across those different switches as well. So broadcast, again, is everybody. Multicast is just a few. And then unicast is one module. Now, modules are required to support at least, usually at least two MAC addresses. They can support more. One of them is just when they want to get a message directly, direct, and the broadcast address, which is all Fs, by the way. And then multicast, they need to support that. So potentially they could be part of various multicast streams. So why can't you just probe Ethernet? So as I mentioned, Ethernet is full duplex, meaning when you're talking about that one wire or that pair, that twisted pair, two modules can communicate simultaneously. They could be synchronous, they could be asynchronous. You just don't know. Because of that, the data is basically the sum of these two communications. When we want to try and connect to that, if you could get a probe that would work with infinite resistance, which generally doesn't work. I've never seen it work. I've even seen videos where they connect a oscilloscopes and you just see little blips, but they're not the correct blips. You wouldn't be able to tell the difference between module A and module B, or device A and device B, because it would look like it's encrypted. Even though technically they're not encrypted, it would look like they're encrypted because, again, they're communicating over each other. So how do we see this communication if you want to test this? So for that, we would need to do what's called an active tap. An active tap is really where you need a device that supports two channels of that same protocol, and you basically run the communication through the device. Now, when you run it through the device, so here we use like a GigaStar, for example, which allows you to do one tap, out of the box at least. We would have to break this connection somehow to be able to see that communication from device A and device B. And then the device will actually let the data go through, so the system still acts normally. Now, when we say break the device, I don't necessarily mean literally cut the wire. Generally, what I see is most teams, what they do is that they'll take the connectors from here and they'll make up a harness where they can use it between this device and the tooling. When you're doing something like that, it's actually kind of good to do the actual connectors. What I've learned over my years of testing, from being in automotive, is that we want to use the connectors in the vehicle so that we can use this in the bench, but we can also use this in a vehicle. Whether it's production vehicles, whether it's development vehicles, I can use the same exact tooling without having to really develop everything. Now, I do see a lot of benches where they use, different connectors for the bench, but ultimately they're still swapping out connectors to put the system back to normal or be able to connect the tooling. So this is one of the tools that you can use. Okay, I don't see any questions, so I'm going to continue. So some of the tools that we offer for Ethernet is a GigaStar, which allows you to do a 100,000-base-T1 tap. It also can act as a media converter. So when I mentioned the moons, the RAD moons, they act as media converters. This could be one that could be used for that as well. Generally, when you're using this, you're usually going to use it more for the tap. Though potentially you can also buy it supports this thing called an SFP, small form pluggable. And it's kind of like a little cartridge on the other side. And this allows you to add different versions of Ethernet. By default, it comes with 1,000 base T. However, you could buy different SFPs to do also another 100 or 1,000 base T1, for example. So this potentially could do 2 taps. This one also supports 6 channels of CAN FD and one link channel. Other things that you can use would be like a RAD Galaxy. This would allow you to do 6 taps. And it has all 8 CAN channels of CAN FD. And I don't remember this one has LIN. I don't remember this having LIN. And then this one is our newest device. This one won't be out till maybe December when we expect it. And so the Galaxy only does 100 base T1, for example, but the Galaxy 2 will do 100 or 1,000 base T1. This one is not quite available yet. Like I said, this will be available around December, so we expect it. So this will be our newest device. Okay, so that's enough for the Ethernet portion. Hopefully it gives you just enough information to kind of understand where we're kind of going here. So the next part we're going to cover now is the background motivation for 10BASE-T1S, sort of the why. So the features in vehicles, features and functions are just continuously growing. During my time at one of the OEMs, the features never stopped. There was always new features being added, new functionality, and so it just doesn't stop. And there's some subsystems that just have more change than others. Some are because of regulations. Some are just because someone came up with more features. So they're not just non-stop. So essentially, a lot of these things can only do so much. Link can only do so much. So you need things that are bigger bandwidth. So this is sort of what 10BASE-T1S comes in. Be able to take advantage of that Ethernet, be able to do the 1500 bytes of data, as opposed to the 64 bytes of data, and do it also at a faster speed. One thing that's been found is that most ECUs or most communications in the vehicle don't really need to be above 10 megabits. At least about 80% of it don't need to be above that. Or, most of it can be below that. So using 10BASE-T1S allows you to kind of start getting maybe rid of or reduce the need for gateways. So when we look at the picture on the left side, this is a heterogeneous network. What this one does is that this is a gateway along with a switch combined. And so when we look at the left part of this, this is a CAN-FD network. And then the right side of this is Ethernet. So there's three channels or three networks connected to three modules. The problem with the gateways is that they require complex software and is never-ending software. And so knowing that features are always being added, that means usually there's new messages being added also to your systems. So if you're doing any kind of bridging between like CAN, for example, to Ethernet, there's got to be some software that needs to manipulate that data in order to make them work. And so if you're adding new data, that means you have to change the code in the gateway. It might not be complex code, it might be fairly simple, but it still requires change. So if you add 10 new messages, that means you need to add change for those 10 messages. Generally, most of those are not generic changes because they're all unique in their own way. So you can't not usually do that in a generic way. So really the focus is to try and be more Ethernet, where you get more of a homogeneous network. So the right side network is a homogeneous network where all of it is Ethernet. If you notice the picture, it looks very similar to the one on the left. And that is because of what 10BASE-T1S is meant to do. So 10BASE-T1S, if we look at it here, it's still Ethernet, but it still connects like CAN. And that's sort of its appeal, that it's connecting like CAN. So if you go back to what I said earlier, when we talk about normal Ethernet or other forms of Ethernet, not so much normal, but other forms of Ethernet, you need a point-to-point connection. But when we talk about 10BASE-T1S, you notice that it's one module or 4 modules connected to one connector. This is also known as a PHY, or physical, short for physical. So you only need one PHY to connect to all 4 modules, where the other ones, where these 3 modules need an independent or a connection to each one. So this is sort of the appeal of 10BASE-T1S. So some of the goals for 10BASE-T1S is to compete, from a cost perspective, is to compete with CAN-FD. So try and reduce the cost of wiring, because these wires can get kind of expensive, as some of these connectors are not exactly cheap either. I have volumes that definitely get cheaper, but they're not exactly cheap. Because I was looking at one of the HMTD connectors to purchase just maybe a pair, and they were about $5 a piece. And it's like, wow, that was even before shipping. So they're not exactly cheap, unless about thousands of them or millions. So by using 10BASE-T1S, it allows you to use kind of IP everywhere. So it allows you to simplify the networks. So if you remember what I mentioned about the MII, the Media Independent Interface, here we don't need complex gateway here because 10BASE-T1S is an Ethernet network. So here, when it gets to the switch, once it gets passed over to the second layer, it's just an Ethernet frame. And so from there, we can just copy it over, assuming it passes the correct rules to pass it over to another network. And it just copies it over and encodes it into the new format. So there's nothing special that really needs to be done. These switches have been around for quite some time now, that there's not a whole lot being added. That doesn't mean the switch software doesn't change or isn't being changed. It's just not going through huge changes like I see with like gateways. Yep. So the other thing that's beneficial for 10BASE-T1S is it offers this thing called POODLE, or power over data lines. So it allows you basically to send power, battery power or battery voltage and ground to the same power connections or through the same communication lines. So essentially, you can now reduce some of the wiring on the vehicle on top of that. The only drawback to this is that there'll be limitations to how much power they can use. This is something that's already being used, like in A2B, for example. They can power off the microphones with the same power, with the same communication links, so it reduces cost. And of course, use multi-drop, so use the same as much of the same wiring, and use the least amount of PHYs to still get the benefits of Ethernet, but at the same time, it reduces the cost. So 10BASE-T1S can be half duplex, and it can be full duplex. If it's full duplex, it will be point to point, meaning only two modules can communicate in that system. However, really the advantage of using 10BASE-T1S is really to use it in half duplex. Half duplex means, just as a refresher, is that it's one module at a time. So we can have now more than one module here, but only one module, or it is a bidirectional system, but only one module can talk at a time. So you kind of go into like what CAN is doing. But it does work a little bit differently, so I'll cover that here momentarily and how that communicates. Because it is a slower system, it doesn't need all the DSP fancy stuff that other higher speed Ethernets do. So it does simplify some of that stuff. It is a self-clocking system because it uses this thing called differential Manchester encoding, which is self-clocking. We'll talk about that here momentarily a little bit more. Okay, so let's start talking more about 10BASE-T1S itself now. Or because my notice getting dry a little bit. Okay, so 10BASE-T1S is a single twisted pair. It is not shielded. So you can see here from the picture, there's just a single twisted pair. It does use this thing called a PLCA. PLCA is a physical layer collision avoidance method. So this is the method that it uses to avoid collisions on the bus. I'm gonna talk about like CAN-FD and Lin, how they kind of work a little bit to give you a background, but this is the method. We're gonna deep dive this here in a moment, what this really means. It is a deterministic system, meaning you will know when the modules are going to communicate. You'll know the order that they're going to communicate in. There's aspects that you'll probably hear me talking about that will make it less deterministic. No matter what, the order will always be the same. Some things that could change the deterministic portion of it can be, if a module decides to send 46 bytes of data versus 1500 bytes of data, because they will take a little bit more time on the bus. But ultimately, the sequence of modules will always be the same. One thing from these systems is that it is max of 8 nodes. From testing this, at least on my setups here, these PHYs that the manufacturers are making, like ADI, Microchip, Texas Instruments, they actually can support a lot more than 8. So this was really more of a initial requirement limitation. Though I believe most of the manufacturers or OEMs are going to kind of stick to this number for the time being. We'll see what happens in the future if they'll expand. But as of right now, at least from a specs perspective, it is 8. But again, they can't support more. And as mentioned earlier, it does support PUDO, so the power over data lines. Now, one thing that's interesting about this bus is that it communicates at 12.5 megahertz, but the actual data throughput is actually 10 megabits. So it's a lot slower in data than what it actually transmits on the bus. And the reason is that it uses this 4B, 5B, or 4-bit, 5-bit encoding. I will talk about what this means here momentarily, because there's a little more to it. And I have a couple tables to hopefully help explain some of that. The other thing here is that from a wiring perspective, so the edge nodes, as they're known, the most extreme points, those are known as edge nodes. They do use 100 ohms at each edge. Now, one thing to understand is that the termination of this is significantly more sensitive than CAN. So if you're used to working with CAN, you can make it work with just a 120 ohm resistor, and you'll probably be okay. You can add the second resistor, and it'll still be okay. You can add a third resistor, as I've done it accidentally, and still work okay. I've seen systems where they added four 120 ohm resistors, and it still worked okay. Maybe not perfect, but it still worked okay. It worked good enough. Here in the system, if I remove a resistor, it stops working. If I add another resistor, meaning I add a third one, it stops working. So the resistance here is extremely critical that you get it right. Otherwise, you will have problems. Twisting, make sure that you have not too much wire that's untwisted when you get to the connectors. It is definitely more sensitive to this. The other drawback of this, at least based on my picture here, is that if I connect to this line, to the main line here, you only get 10 centimeters. So it's not very long. So this will probably be more of a limitation that you'll see in benches, not so much in a vehicle. In a vehicle, what I would expect to see is really more this type of wiring where they're daisy chained. So essentially you go from one module, they get wired off internally. And essentially, if you want to really kind of look at it, this 10 centimeters is really inside the module, not so much on the outside. So this allows you to connect all these different modules together. Now, this doesn't mean that the drop nodes that are in the middle will stop the communication. As long as they're plugged in, they should still pass the communication. There's nothing that should be gating that message. It should just be physically connected inside of it, inside the circuit board. So if you unplug this, the communication to the rest of the vehicle or the rest of the system will stop. As long as the module is plugged in, it should still communicate. This is more what you should expect to see in vehicles. Probably even in benches as well. So just so you get a sense of how other protocols deal with collisions. So Lin uses this master-slave methodology, and he uses a schedule table to determine who's going to communicate. So it's an extremely deterministic system that the master determines who's going to communicate. And in this case, if the module is connected, it's actually required to communicate when it's told to communicate. There's no ifs or buts. It needs to communicate when it's told. FlexRay is a little bit different, that everything in the system is pre-programmed in advance. So the modules themselves know when they can and cannot transmit. So also somewhat deterministic, somewhat. CAN uses this thing called, it uses a non-destructive arbitration process. And what this means is that the modules will actually attempt to communicate at the same time. And whoever has the lower arbitration ID or the lowest message ID, what it'll do is whoever has the lowest message ID will win. And that's who gets to communicate next. And after that's done, it goes through another process determining who's next again. And then it does this over and over. So if you ever work with Vehicle Spy or other tools that tell you, the approximate rate of the message, they'll vary. So if you have a message that's meant to be about 100 milliseconds, for example, you'll see it vary between 90 or maybe 110 milliseconds ideally. However, it can be a little bit more or less depending, on how busy this bus might be. So because of that, you can't guarantee that latency. Sorry, I just saw that there's a question. Can you give an example where a half duplex of 10BASE-T1S could be used, where multiple ECUs are connected and only one gets to transmit? I'm not sure I understand the question. So an example of half duplex system is really most systems that are going to be using it right now. That's where it's going to be used. As far as I know, the spec isn't ready to do full duplex. I think it's all meant to be half duplex at all times. And then another question was where multiple ECUs are connected and only one gets to transmit. So an example where maybe only one module gets to transmit is if your system is misconfigured. I'll talk about that here momentarily more on how that works. But if you have a system that's misconfigured, then some modules will not be allowed to communicate. Okay, so so when we talk about multi-gig, 100 base T1, 1000 base T1, or multi-gig T1, yes, the presentation will be available after the webinar to whoever signed up for this. So when it comes to multi-gig, because it is full bandwidth, there really isn't any point that you have to worry about collisions. So because they can communicate simultaneously, there is they're going to essentially cross-talk at the same time. So for that perspective, the only time they can't really send another message is because they're currently sending a message, or there's usually minimum wait time between one message right after another one. But other than those two, they can be very chatty. Okay, so let's talk about the PHY or the PLCA. So PLCA stands for PHY level collision avoidance. Now, without a doubt, from all the trainings that I've given about this is probably the hardest one to kind of put your arms around, or really to kind of understand. So PLCA, like I said, what it stands for. Can you have two masters on a limb bus? No. If you do, you're going to have some communication issues. It's meant to have one master and then multiple slaves. Okay, so in PLCA, the nodes are given an ID number. Now, the ID number actually tells you the order in which these modules are going to communicate. Now, node 0 will have a special meaning, and it actually has the name of the coordinator. So it actually is responsible for coordinating the PLCA cycle as we kind of know it. So you can have a couple more modules, and so what happens here is, like I said, they have all different numbers. So if you have 8 nodes, they start with 0, and they'll go up to 7, and so they'll have a different number. Sorry, the questions are kind of throwing me off here. Okay, so here, so each module will have a node ID. So the node 0 will have a special meaning, which means coordinator. Coordinator means it's going to send this special thing called a beacon, or it's a special symbol that goes on the bus. It's not a message, but it is special bits that are sent out to tell the system that we're about to initiate a round of communication. This beacon is essentially telling all the nodes on the bus that they need to reset their clocks or timers or reset their count, because each node is actually responsible for keeping track of when it needs to transmit after the beacon is sent out. After the beacon gets sent out, this thing called the transmit opportunity comes out or opens up. It's not actually a message, it's just sort of time that elapses. And the transmit opportunity name sort of is a little misleading, because it kind of implies that the module needs to transmit its entire data in this time frame or this TO, and it doesn't. All this TO really means is that this is the time for the module to begin to communicate. In other words, it's its way to determine or tell the system that it's in fact going to communicate. If it doesn't communicate, the TO will expire, or it will time out, and then the next TO would begin. So a module is actually not required to transmit during its TO. It can, but it doesn't have to. So once the beacon goes out, this TO begins, and the length of time is actually configurable. By default, it uses 32-bit time. And it's basically multiply 32 times 80 nanoseconds, and that's your time, which is about 2.5 microseconds, if I remember correctly. I can't do the math in my head right now. But so it basically has that much time to decide if it's going to transmit. And it'll begin to transmit during this time. If it doesn't transmit, a new TO begins, and the next module comes out. Now, a beacon does not come out for every module. It comes out one time until all the modules are done communicating, and then a new beacon comes out. So it's one beacon for communication cycle. So the beacon will go out, TO begins or opens up, first module can communicate. If it communicates, it starts to communicate, starts sending its data, its packet, or its message. And after it's done, a new TO begins. And again, the module that's next needs to keep track that it's next. So it needs to know when this module either allows the TO to expire or time out, or it needs to know when the module is done communicating, so know that it can now transmit its message if it needs to. And so it basically goes down the line until it finishes down to the last module. Once the last module is done transmitting, or it lets the time expire, then a new beacon will come out to begin a whole new cycle of the communication. Okay, hopefully that's clear. Usually this is by far the hardest one to understand. Usually in class, I usually use people as modules, and I kind of walk through it, and I find this one a little harder to do here, at least in presentation. Okay, so hopefully everybody's okay with that. So the encoding on the line, it uses a 1 volt peak-to-peak signal, which has a 20% margin of error. Now in communication, 20% is actually quite huge, but in this case, it doesn't really matter too much, because if you're talking about LIN or CAN, those usually use voltage thresholds to determine a 0 or 1. In differential Manchester encoding, it doesn't use voltage thresholds to determine if it's a 0 or 1. It actually uses transitions. So here on the bottom right here, we have a plot of a beacon. Now, a beacon actually comes out 5 times. In this case, we're only taking out the symbol 1 time, just to kind of demonstrate what happens. But here, what happens is each of these boxes is basically a bit. So when we see a data bit go up, and it kind of just rolls over to the next part, that's a 0. When we see it roll down and roll back up again, also 0. So here is another 0. Now here in this 4th bit, you kind of see that it kind of slashes to the middle or something kind of exciting happens in the middle. That really means this is a 1. So this is a transition. So long as it happens within this period, within this time, it's a 1. Another thing to understand about the system, in case it matters to you, is that this uses the least significant bit for data. So whatever you see on paper, whatever you see on paper, reverse it, and then that's what you'll see on the bus. Okay, so I can. So yes, so because it's a multi-drop system. So there's a question: is this so like CAN in 10BASE-T1S? All you see is know when the given ECU is talking. Yes, because they'll see the communication. So if they start talking in their transmit opportunity, all the modules get to see that are in that bus. That doesn't necessarily mean that it'll get past the switch, but in that system, all will see it just like you see in CAN. Now, whether they consume it or not, is a different thing, but they will see the communication. So how would they know that their time to transmit is based on, once again, if it times out, so if the initial TO times out for the first module, then the next module knows that it timed out because it has to keep track of that, and then it knows that it can start transmitting. Otherwise, it needs to wait till it finishes before it knows to transmit. I'll talk about this a little bit more because there's a little bit more details to this on how that handshaking kind of works out. Okay, so here we go back, and if we do a 1 divided by 12.5 megahertz, which is what we should be transmitting on the bus, we should get 80 nanoseconds. So each bit here should take approximately 80 nanoseconds. Realistically, I've never seen it at least transmit at 80 nanoseconds. Usually I see it between 82 and 90 nanoseconds. I think I saw last time a bit take about 100 nanoseconds. Usually the first bit is the slowest one. Usually after that, it gets down more closer to the 80. But usually it's still in the low 80s, 81, 82, maybe 83. Okay, so let's talk a little bit about the 4B, 5B encoding. So what this does is that it actually allows you, or what the system does, it actually transmits, for every 4 bits it wants to transmit on the bus, or that it wants to transmit, the bus will actually see 5 bits. What this allows the system to do is that because we're using 5 bits on the bus instead of the 4 bits that we normally transmit, it allows it to represent more symbols on the bus. So normally the 4B, if you did 4 bits to 4 bits, you would just represent the normal communication. What this allows us to do is add additional symbols or special symbols to the system to be able to see, to do some handshaking on top of it. So the layer 2, for example, once you transmit 4 zeros that are in sequence, what actually will be in the bus would be a 11110. And so you can see the list of how this looks. So this table in the middle, this is your normal communication. Everything to the right is your special symbols. So if you have a frame that's this big, before it gets sent out on the bus, by the time it gets sent on the bus, it's going to increase a little bit more. So it takes a little bit more time. So when we look at the actual frequency that transmit on the bus versus the actual data, it's because of this. Because it's transmitting more bits on the bus than the actual communication needs to be transmitted. And that's just because we need to be able to represent more symbols. And that's really the special symbols. So I'll talk about that here momentarily. So there's a question that says, how does node 0 know it is time to transmit the beacon again? So it's all based on settings. So the system knows how many modules are in the system. So if there's 8 modules, it needs to be configured to be 8 nodes. It also needs to be configured with how long the transmit opportunity is. So if it's 32 bits, or if it's something lower, or if it's something greater, it needs to know that. So if nobody transmits, it basically just calculates the timeouts, and then once they're all expired, it knows that it needs to send out the beacon again. If there's communication, each module will actually say when they're done talking, and then once all 8 modules, assuming it's 8 modules, once the 8th one is done transmitting, again, the coordinator knows that it's done, so it sends out the beacon once again. Okay, so let's complicate this a little bit more. So there's a little bit more detail that I didn't cover on the first slide on how this transmits. There's actually a little bit more handshaking than just a beacon. So the beacon's still the same. It's still the beginning of the sequence. So the coordinator sends out this beacon that happens to be this symbol here. So if we go into the beacon, happens to be 0, 1, 0, 0, 0. Keep in mind that it's least significant bit. So what we see here on the bus will be reversed of this. So this actually goes out 5 times. That is not configurable. That is per design. So you will see that beacon come out 5 times. So you essentially see 25 bits come out. And that's telling the system, that we're about to start around communication. Once that goes out, TO opens up for the first module, which happens to be coordinator. And then, so if it decides to transmit, it begins by sending a couple of special symbols. Those special symbols are basically commit, SSD, SSD. SSD stands for start a stream delimiter. Now, by starting the commits, that means that the module is in fact going to take its transmit opportunity. But you'll normally see at least minimum of 2. It can send a few more. The reason it can send more is that maybe the second layer, or maybe the first layer are not quite ready to transmit. They're still in the process of encoding that. And so it might need to hold off the bus ever so slightly before it sends out the bus. So you might see a few more commits. I've seen some in the 60s. I've seen some in the 30s. It just depends on how much time it needs to prepare, and then it sends out its message. And then once you see the 2 SSDs come out, right after that, you'll actually see the packet or the message for that node. Once the node is done communicating, it actually sends another set of special symbols denoted here. And those special symbols are ESD. It's end of stream delimiter and end of stream delimiter OK. Once you see this, that means the node is done talking. That means there's nothing else that's going to come out. After that, a new transmit opportunity begins. Again, a place for the module to decide that it's going to transmit. And if it's going to start to transmit, it goes ahead and sends it commits. And that basically says it's going to transmit. If for some reason something happens that it changes its mind, it'll just send a bunch of commits. It'll do the SSDs and they'll immediately go into the SSD, ESD OK if it's not going to be ready on time after that. Okay, so the handshaking again is what tells us when it's going to communicate and when it's done communicating. So that's how we know. So the special symbols tells us that it's done. So this part is just for reference purposes. So a beacon here is 0, 1, 0, 0, 0, 0. And then on the bus, we'll see reverse. We do have a software called RAD-Mobile that will actually allow you to take a picoscope and a differential probe. And basically, it'll help you decode all this data, as opposed to look at something like this, maybe where you do just a picoscope or an oscilloscope. This data can be seen in an oscilloscope. When we do the hands-on training, usually you get to play with this and see the actual beacons and have fun decoding it. Usually fun decoding once, maybe a couple bits, but after that it's not fun, especially if you have a whole message to decode. That could take you some time to do it manually. So we do have a piece of software that actually helps you decode all this data. And in case you ever have to look, if you ever have to go look at a trace of the actual bus, an actual basically scope trace, this is just so you know what it looks like. So this is what a beacon should look like. So this is 25 bits, or beacon sent out 5 times. The beginning of frame, so you see these 2 commits followed by 2 SSDs. Though these commits can be more than 2, in case there's the module is not quite ready to transmit. Then when it's done transmitting, you should see this ESD and then followed by ESD OK. So RAD-Mobile again is just a software that kind of helps you decode all this data. So it puts all this nice and easy. I know when I first started teaching this class, I used to use a picoscope, and this was done manually. And then this came out, and then this was great because then we can actually see more. But nowadays, we have Vehicle Spy kind of doing some of this data without looking at the trace portion of it. It actually decodes the symbols for us. And so if we go into Vehicle Spy, if you've ever used Vehicle Spy, or if you've never used Vehicle Spy is a software that we sell that works with our tools. So here, if I look at the scope trace, so if I try and look at this, for example, here it gives it to me in words rather than a scope trace, right? This can be kind of interesting to see, but not necessarily the most fun thing to do. So here I can go into my trace or my messages view in Vehicle Spy, and then I can see like the beacon. So here it tells me the symbols that tells them to me in hex value. So here I can go to my handy dandy table on the right side. I can see 08 equals beacon. And here in the length that we see that it comes out 5 times. So here, like for the commit, we see it comes out 2 times, SSD 2 times, and then the packet. Packet is just your message. And then once it's done sending the message and it's done communicating, it's done the sequence, which is the ESD followed by ESD OK. And that tells you that it's done communicating. And then you can see the new sequence begins. Okay, so burst mode. So if for some reason your module has data diarrhea, meaning it's just got a lot of information, it's got to get out, burst mode is what would be used. The recording will be posted on YouTube at some point. So burst mode is a way to send more than one frame. Now, the burst mode is configurable, meaning a module can be allowed to use it or it cannot be allowed to use it. And if it is allowed to use it, it can be configured to how many frames it can send sequentially. So the maximum we can send is 255. If it's not allowed, it would be 0. So that needs to be configured per node. The sequencing is very similar to a normal communication. You still get a beacon. You still get a transmit opportunity. The beginning is still the same. So if it's going to commit, if it's going to send a message, it starts with commits, followed by the SSD, the start stream delimiters, followed by the message frame. Now, to this point, you do not know if it's going to be a burst mode. You will not know that until it's done communicating that message. Then it'll go through a different sequence to say that, hey, wait, there's more. So when there's more, you'll see the sequence. It'll send this ESD OK, followed by another ESD OK, followed by more commits, and then SSD. And that's how it tells you that there's going to be at least one more frame. Now, from this, the way it communicates, you will not know how many frames it's going to send. You have to wait till it's done to know how many frames it actually sent out finally. There's nothing in the format that tells you it's going to send out 255. There's nothing that tells you it's going to send out 2. There's nothing. It's just you got to wait to be able to count them all. So that sequencing is sort of what you need this. So once it's done communicating, there's a little bit longer sequence to say that it's done. And so from that sequence, we'll see this ESD OK, followed by a couple commits. And then you'll see this ESD and then ESD OK. And that's the module saying, I'm done. Now, just because the module sends out multiple frames in a burst mode, that doesn't mean it takes away from a TO from the next module. And this is where you start going, well, maybe this is not a deterministic system. Well, from that perspective, you would be right that it's not. However, the next module still, if it's module 1 that's communicating, node 2 doesn't lose its opportunity. It just gets pushed back. Okay, so that doesn't change the order. It just might delay the entire PLCA cycle. So here's just more reference material. So the reference materials, again, if you ever need to go back and look at the stuff, so that's what the beginning of a burst mode looks like. The end of burst mode, what it looks like. And then from a vehicle spy perspective, here you can also see the sequencing. So here we see the beacon come out. We can see if the first message begins by doing commits. We see the first packet, which is your message. And then you'll see the start of burst mode, which is here, which is DSD OK, followed by the commits, and then SSD. After that, you'll see the second message. And here, vehicle spy will also tell you the burst that it's in. One thing I also forgot to message, because the system is deterministic, meaning we know the TOs, right? We know the beacon when it goes out. Vehicle spy will also tell you the node ID, who's transmitting. But it also tells you the burst mode. So here I can clearly see that, at least in this example I came up with, it sends out 2 messages back to back. If I use 255 messages, it'll tell me it sent out 255, but we should also see all these sequencing. Now here in this message here, before the packet goes out, we see that it sends out 36 commits. So before it sends out the packet. On this one, before it's done, it sends out 63. So this can take a little bit of time on the bus. Not a lot, but it will take some time. A full message, 1500 bytes of data, takes approximately 1.22 milliseconds to go out on the bus. So it's actually quite fast to send out a full frame. Just making sure I'm not forgetting something important. So the transmit receive process, the way it works is that it starts at MII, which is your layer 2. And then after that, it goes into layer 1, which just goes through the scrambler. Scrambler is basically a way for the microcontroller or the PHY to determine the best way to send the stuff on the bus. So it reduces the EMI, electrical magnetic interference. After that, it does the 4B 5B conversion. So it takes a frame that's yay big and makes it a little bit bigger. And that's what's going to go on the bus. And inserts any special symbols, such as like the commits, for example, the SSD and ESDs. So the starter stream delimiters and the stream delimiters. And then puts it into a format that it can actually be sent on the bus. In other words, it serializes it. So in this case, the zeros and ones. And then finally, it puts it into the actual encoding that goes on the bus, which happens to be differential matrix transistor encoding, or DME. Once it gets to the receiving module, it basically goes in reverse, and then it goes back to the MII, which can now be used as to go to the next step. Now, this question I get asked a lot. Well, what happens if my coordinator dies? Which is a good question. So it'll revert back to this thing called this CSMA/CD, Carrier Sense Multiple Access Collision Detection. That's a bit of a mouthful. This process or this methodology is not new. This has actually been around for quite some time. As far as I know, this goes back to when Ethernet first got developed. This is the way it actually worked. Now, all PHYs actually still support this, even though it's not really used in full duplex anymore because it doesn't need it, but it's still supported. So 10BASE-T1S will definitely use this if the coordinator dies. And the way this methodology works is that multiple modules will try and transmit at the same time. And if they detect any collision, each module would do, or each PHY would do a random backoff time. And then they will attempt to re-communicate again. And they'll keep doing this until there's no more collisions. And then basically this process goes over and over. So it's not exactly the most efficient of methods of communicating, but it is sort of a nice backup or reasonable backup to this. Okay, so let's talk a little bit about zonal architecture, specifically some of the challenges that you're going to face. And zonal architecture is really the piece that's going to be supporting software-defined vehicles, or SDV. So here in the pictures, we see that we start off with what's known as a domain, and over on the right side is a zonal architecture. You see on the left side, there's possibly a lot of wiring, a lot of cross communication going around the vehicle. So really, the zonal architecture is really an optimization of wiring and modules, trying to reduce some of the modules that are needed. So this reduces weight, this reduces cost, hopefully simpler assembly time, but it's really an optimization. That doesn't mean, wiring, but people that worked in wiring didn't optimize this as possible, but definitely that you definitely have extra communication wires going around that maybe didn't need to be there. So really, this is really kind of taking a step back and kind of going, what do we need to kind of improve this process? So this is just an optimization. So the other part about zonal is that everything becomes centralized. So you'll have a central compute module. So all the brains that used to be in individual modules now kind of become dumb, and all that really goes into a centralized compute module. Just so you know, centralized compute module doesn't necessarily mean literally in the middle of the vehicle, because some of these modules are going to be quite big. I don't know if they'll fit in the center console. They might. I don't know. But they'll be somewhere in the vehicle, and that's where most of the decision making will take place. That doesn't mean that the outer modules on the legs of these zones or the corners of the vehicle won't make some kind of decision. It's just most of it will be made in the central compute module. So here, so domain, when we talk about domain, it's really the different domains that exist, like infotainment, powertrain, body, HVAC, chassis. Those don't really go away. That's still going to exist. The only difference is that they're not going to be grouped based on zones or based on domains. Now, I haven't really seen a lot of these be necessarily domain-centric now. I know some of the older architectures that I work with definitely had some networks that were very domain-specific. But not necessarily all modules were domain-specific, or the communication lines were necessarily domain-specific. But there's definitely in the older days, they were definitely very domain. As we get more into the now, some of this stuff has kind of crossed a little bit, but they're still kind of exist. So the zonal really goes in. You still have, like I said, you still have all these domains, but they'll be more based on location. So you'll have zonal zonal controllers or these zonal gateways or zonal switches that will exist in the vehicle. And these will basically take all the data that's centralized and put it into the areas that they need to be. So some of these will be like I/O extenders, if you will. One thing to understand about zonal is that the backbone will always be Ethernet, meaning all the communication in between all these main systems will always be Ethernet. So Ethernet will be a big part of your life if you're going to be working with zonal architectures or SDV, if you aren't already working on these. Now, transition from domain to zonal, will it happen 100%? That's really hard to say. I would say probably not. There's definitely systems that will probably still be, off on separated, like ADAS. ADAS, in case you don't know, it's advanced driver assistance systems. So that might still be separate, just because of it might add a little bit of latency that maybe they don't want to do. But that doesn't mean that it won't move 100% to zonal. It just depends. I don't think it'll transition at least all in one step. I'm sure we'll see a hybrid of this over time, at least initially. Now, testing, domain was fairly easy. So if you've been around testing for some time, the domain is actually fairly easy. You connect to a bus, maybe a couple buses. Oh, sorry, I missed your question. So how do the coordinators know the coordinator died? Well, there would be no beacon. There might be power lines that turn on as a backup system. They might turn on an activation line that tells the modules, hey, maybe you should be awake. So that might be one way. So in domain testing, it's fairly easy. Connect to a bus, maybe to connect to a couple different buses, and you see most of the communication. You can probably connect to a couple, 5, 6 buses maybe. I see a lot more buses now. You might see somewhere between 60 to 80% of communication. There might be the few folks that need to go to a little bit deeper, might need to connect to a couple more buses, like specifically like Ethernet, to see what they need. But from my experience, most people connect to a couple buses and they're able to see everything that they need. So fairly simple. Usually one tool is sufficient to do what you need. Again, life is simple here. When it comes to zonal, it gets a little bit more complicated because you're going to have a lot more protocols to deal with. In the past, you probably dealt with maybe CAN, LIN, maybe 100 or 1000BASE-T1. And those were probably the dominant systems that you saw. Maybe E2B you would see occasionally. And there's definitely other protocols that exist. There's wireless battery management communications that exist. So there's definitely more than a few communications. But when it comes to zonal, you're going to have more things to look at. So you might require more than one tool in order to be able to see all that communication that you need. So here, if I want to connect to just one corner of the vehicle or one leg of the vehicle, I would need at least 2 tools to be able to see all that communication. So if I wanted to do an active tab for 1000BASE-T1, for example, if I need to see a LIN message, LIN channel. Here, if I'm using a Comet2 or Comet3, I can have LIN as well, 10BASE-T1S and CAN-FD. So I would need at least a minimum of 2 tools, at least at this very moment, to be able to do that testing that maybe in the past, one tool was sufficient. So you might need to do that. You're probably going to see a little bit higher throughput too. Where it gets kind of complicated is when you have to look at something from the beginning to the end. Now, I was laying in bed one late night trying to come up with an example, and I came up with something I've seen kind of over and over. There's sensors now that are learned for brakes, and then that transmits over to turn on tail lamps. In the past, you would probably see that in maybe like the body control module, control the lamps directly. There's really not a whole lot of communication. There was probably a message that went on the bus that said, hey, the lights are being requested to be turned on. And that was it, plain and simple. Really, the validation was look at the tail lamps turn on, and you're done. But here, if I really wanted to look at the entire system from start to end, if I wanted to look at all those buses, so if you said that I need to look at all the communication, which I often hear, I want to see all the communication, you might need to do something like this. So here, I could use like a RAD-IO analog input to allow to be able to see the brake sensor being pressed, if I care about that. Then I can take like a CAN hub and convert that over to CAN-FD message if I want to record that data, if I need it. But from there, a module that reads that value will translate that to some type of communication. In this case, in my example, I'm using 10BASE-T1S. So I would need to be able to see that communication. After that, it goes through a zonal controller or zonal controller. And from there, I would need to do some active taps in order to be able to see that communication go from the zonal controller to the central compute module to see what that looks like. And then once the central compute module makes a decision to turn on the lamps, then I would need 2 additional taps or active taps to be able to see what gets sent to the other controllers. After that, I would need to see what goes between the zonal controller and the first ECU. If it's a I/O extender or if it's something different, that might be 10BASE-T1S. And then finally, the ECU might control the tail lamp either through CAN or maybe LIN. A lot of these lights are no longer just simple I/Os anymore because all the choreographing of lighting that happens now, a lot of them are now using LIN or CAN FD. So in order to be able to see that, I would need at least 2 tools minimum to be able to see that. If I wanted to see the sensor, I would need at least 4 tools to be able to see that. Now here I'm using a Comet 3. If I was using a Comet 2, I would need at least 2 of those. But here now I can combine some of that. The other challenge you're going to see here is that you can kind of start seeing that these are corners of a vehicle. So you might need to take the vehicle apart a little bit more to be able to see all this communication. So this in itself is going to be more work. When I last tested, I used to take maybe 1 panel off, maybe 2 at the most. Real simple. Unless you're working like the sunroof module where you have to take the whole headliner, that's quite a bit of work. But assuming you're not working that, you took 1 or 2 panels off and you can see everything you needed. But definitely this is going to be a new challenge for you, having to take more of the vehicle apart. And if you truly want to see all the communication, you might need more than 1 tool, and you'll need more points to be able to connect to. Okay, so some of the tools that we offer for 10BASE-T1S. So we offer a Meteor. We usually use this for our training. This one allows you to do basically can be used as a meter converter. So this can be used from 10BASE-T1S and connected to my computer and be able to see that data. When you connect, this connects to the computer through the USB. And once you connect it to the computer, it enumerates as an Ethernet port or an Ethernet NIC. So you can use like Wireshark, for example, to see that data. So like I was showing you some of the pictures where Vehicle Spy will show you some of the special symbols. This one would not be that because it's not a message. So our tools are meant to work with each other to be able to provide that data. But something like this would just give you the data that's coming from the normal Ethernet traffic. Also really good for learning because this can create real simple simulations. You can't control a lot of the simulation portion of it, but you can control like how much data it sends out. You can, like number of bytes you send out of the frame. You can do burst modes and other little things. They're pre-programmed in advance. Other tools that are available also would be like the Comet 2. That one is can be purchased now. This one allows you to use 2 10BASE-T1S channels. It also has a 100,000 base T1 port. Also has a 10, 100,000 base T channel, 2 CAN FD channels, and 1 LIN. The good thing about this one that's really kind of nice, that's actually being leveraged by a lot of teams that I work with, is that some teams want to take the 10BASE-T1S and output it as 1,000 base T1, because they're kind of waiting for a module to come out, and so this sort of deals the gateway or the zonal module temporarily, at least. And it takes is a couple of clicks, and you can get it up and running. It's not very hard to get up and running. This one also has the ability to do termination for the T1S channels. So you can turn that and off as needed. Comet 3 is the newest one that we have available. This one has 6 10BASE-T1S channels. The rest is sort of the same. The other thing that it does not have is the termination like the Comet 2, but you do get increased channel count. So if you need termination, you'll need to add externally to get that up and running. And then Vehicle Spy, I kind of covered the burst mode, but Vehicle Spy is really meant to allow you to see the data, but also allow you to simulate data. So here, like for this example here, these green dots, I'm simulating this data with Vehicle Spy because it allows me to look at T1S specifically. I can also do some data analysis. These special symbols are not something I have to turn on. I can turn on. I can turn them off if I don't need them. But it allows me to look at this data if I need to do any network analysis. So for example, maybe I want to know if my module's transmitting every opportunity. This would let me do that because I can see the beacon and then I can see each individual message that it sends out. So I can either turn on just the beacon and then see the data, or I can turn on all the special symbols and then see the data as well that's being sent out. Okay, so wiring. So the version of, so I got a question, which with these configurations, what version of eSpy would be necessary? You need at least 3.9, 14, 15 with a Comet 2. If you're working with a Comet3, you need to contact us to get a beta version. That's not expected to come out a little bit later this year, in order to get the Comet3 to be function, if you already got one. Okay, so let's talk a little bit about wiring, because wiring is definitely a little bit more finicky in 10BASE-T1S than it is in CAN. So if you have a Comet2, the Comet2 allows you to do an internal Y, kind of like you would see in the module. So it has an input and output, though technically they're both inputs and outputs. It's just their name to make it easier. And then all I have to do is basically break the connection somehow. Again, I don't always necessarily mean literally break the connection. It could mean just use the connectors of the modules to kind of make a new harness to go into the Comet. And then this would allow me to see that communication. Now here in this example, I'm connecting between node 1 and node 0 and node 1. However, I don't need to connect to this specific location. I can do node 5 and 6, or I can connect between node 2 and 3. So it doesn't really matter because it is a multi-drop topology. I should be able to see all the communication that happens in this network. So I wouldn't be able to necessarily see the communication that happens in a different network that once it gets past the switch, but here within this little network, I should be able to see that easily. This is just so you have so you know how to wire it up. I find this super easy. Usually when I'm working with somebody, I forget stuff, and if I don't have internet, I can quickly open up the presentation. I can see what I need. So here we're using our cable. Here's the pinout plus the color coding for the Comet2. If you're using a Comet3, here are the IX connectors. Same thing, pinout and the color coding for the cable. So in the Comet3, you'll have one connector that has 4 channels for 10BASE-T1S, and for the other connector is two 10BASE-T1S channels. I haven't had time to play with the Comet3 in order to figure out what the wiring should be, but at some point I will have that, and I will probably have it at some point. I just don't know when I'll get a chance to play with one, because I do need to kind of play with it and make sure that I can really understand it to give you good examples to how to wire that up. Okay, so hopefully that explains a lot of things. I'm going to cover some of a little bit show and tell. Normally in class, or my class that I usually teach, it's hands-on. But here, just to give you a sense of what goes on, I'm going to just give you a real basic sample. So here in my little setup that I have at my desk, I created a network. So here my network's going to be configured to 8 nodes, even though I'm only going to use 2 nodes. I'm going to use my transmit opportunity 32. I'm going to have PLCA enabled. And I'm specifically going to use network AE02, automotive Ethernet 2. Will there be a hands-on class in the near future? Usually we post those on our website, where you can sign up for the ones that are on-site in Troy, Michigan. If you're outside of Michigan, ping us. We see what we can do for you. I've actually been taking this class around the world, so there's definitely been requests where I've gone to a couple of different countries to teach this. So don't be afraid to reach out to us. We'll see what we can do. Maybe we're living near another office. We'll get you in contact with them, unless you really want to meet me. Okay, so this is my little network that I have here on my desk. Real simple. So the first part I want to show you is how to configure the Comets. Because the way you configure the tool is a little bit important. So here we have it wired in, and there's multiple ways to get to this. We can go to Setup. We can click on the hardware that gets us into this Nava Explorer. You can also click on this button here, or the button down here from this window. From here, I'm going to open up Nava Explorer to see my Comet2. So here I'm going to select my module, my device that I have. I'm going to click on Connect. And here's where I would configure my device. So here, if I click on this is how I would configure my device to be able to gateway data. In this case, I just have it directly to my PC. But if I need to do a T1S to T1 tap, I would just click on this one here. And now I can gateway all that data that comes in for T1S over to a T1 channel. In this case, I'm going to keep it as independent. Okay, so here, what I want to do is I want to go to AE2, AE3. These are my 10BASE-T1S channels. Now here, in my Comet2, I'm able to do the termination In a Comet 3, you would not have this option. The rest of the options will be the same. Now, what you select is really dependent on what you need. So if I uncheck this, I can get rid of the special symbols on the bus, meaning vehicle spy would not see this. If I need to see those symbols, then I want to select those. Again, depends on what kind of analysis you need to do. If you don't care about the symbols, I would recommend that you turn it off. It's just less data on the screen. And if you're trying to capture data, it'll be less in the buffer. So I would recommend you turn it off if you don't need it. In this case, I don't need termination because I have external termination. And here, how you configure the tool is actually kind of important. So if I want to simulate, if I want to do the coordinator, local ID would be 0. If I want to simulate a specific module, let's say I want to do node 1, I would select node 1. Make sure that you get rid of node 1 from the system if you're going to simulate this. You want to configure it also to be the correct number of nodes. If this is not correctly set, things may start talking out of sequence. The thing that happens if you talk out of sequence is that the module that maybe was meant to talk, if it sees communication from another module, it's actually designed to stop talking or not talk. It'll have to wait till its new transmit opportunity. Also, same thing. So these numbers are very important to know, where it's in line to know when to talk and when not to talk. If I'm allowing burst mode, I would put whatever burst mode I'm allowed to. If I'm not doing any burst mode, it would be 0. So in this case, I'm going to leave it at 0 because I don't want to do that. Okay. Question I'm getting: what if you just want to listen to the communication? Good question. Here, what I want to do, if my system is set to be 8 nodes, I want to put this something greater than 8 nodes. So 9 would be okay, 15 would be okay. That way you just monitor. If you put anything lower, that's within this range. So this would be 7 or below. That means they can actually talk. In this case, if I just want to listen or monitor the data, put something greater than the max nodes. So if your system has 6 nodes, anything above 6 should be fine. Sometimes I would put put a bigger number just to make sure that you're really out of that area. Just again, something bigger, and then you'll keep yourself from accidentally sending anything out. So here, if I do 0, that means I'm not going to allow burst mode. I'm going to turn that off temporarily. I'm going to write settings. Write settings makes sure that I save these settings. If I don't do that, whatever I change here will not be saved. And all I have to do now is click disconnect and close the window. So now here I can go now to run retransmit. And here, what I'm going to do is at the very bottom, I want to make sure that I select 10BASE-T1S, so it gives me the property code is for 10BASE-T1S. And then here, I'm going to erase the buffer. We see that the beacon is coming out here. Now here, what I really want to do is I want to click scroll. So it gives me all those nodes, or sorry, all those special symbols that come out really clearly. So here, what I'm going to do now is in my system here, I'm just going to start doing some simulation. And here we can start seeing there's messages coming out. So if I put pause on this now, I can see the communication that's happening. So here I can see like the beacon. I can see 2 commits. It says 2 right there. I can see the 2 SSD. I can see a message, and then the end of sequence saying that it's done. And then from here, there'll be additional timeouts things that will time out because there's no other nodes in my system. And then the beacon will come out again. So we can see clearly what the sequence is here. So I'm going to stop my simulation here. Now, if I wanted to simulate a message, now here, what I'm going to do is I'm actually going to create a message by hand. Normally, in reality, you're going to use a database to create this. Normally, most people do not create messages that are custom. Normally, we're going to use a database. But here, to keep things simple, I'm just going to create a real simple message. And for that, what I'm going to do is I'm going to go Spy Networks, Messages Editor. Now here, because I want to transmit on AEO2, because that's how I have it wired in, I'm going to select my bus here, and I'm going to specifically select Ethernet. And then I'm going to use AEO2. Now, how do you know which one you use? You really got to go back to the label and figure out which ones you're going to connect to. That's how you would know. So in this case, I wired up based on the AE2. Oh, before I forget. So here's the settings for Comet 2, what you would touch, and then for Comet 3. So if you notice, I don't know if you can tell, but really all that's missing on the Comet 3 is the termination. Other than that, it's the same settings, the same process. So here, I'm going to create a message. I'm going to start by going click plus, and then I'm going to give this a name. I'm going to do this V1's message. From here, I'm going to change the ether type to IPv4. The rest for me, I'm going to leave it as what it is perfectly fine. And then from here, what I'm going to do is I'm going to add a signal. I'm going to do a text message. I'm going to increase the size of this. I'm going to do, how big do I want it? Let's go with 46 for 46 bytes. Click OK. And now I have a message that I can now use. Ooh, I forgot to change this. I want to use text. So from here, what I'm going to do now is I'm going to go Spite Networks, Transmit Panel. Creating in the correct place? I'm creating in the wrong place. I accidentally selected receive. So I'm going to copy this. I'm going to copy this to transmit and receive. I'm going to get rid of it. Okay, there we are. Okay, so now I can go back to transmit panel, which is Spite Networks, TX panel, and here's my message there. So down here now, because I have a text message, now I can put whatever message I want. I normally class someone else is awesome, but today I'm going to be the awesome one. Juan is awesome! Exclamation point. So here I have a message that's real simple. We can see the MAC address here. So if I want to do a broadcast message, I would change the destination source or destination MAC. And I'm literally just going to type a bunch of Fs because that is a broadcast message. The source MAC is fine. What I have here, the IP address is fine. And the ports are also fine. So essentially the ports, in case you don't know, they're kind of like when it gets into a module or a server, for example, you're kind of you're telling it wherever it's getting to, what piece of software needs to go to, what location within the module it's going to be used. So if the MAC address is sort of like the address of a building, the port would be sort of the door inside that building. So it's good enough to get to the address of the building, but it may not be good enough to get to the building. You might still need to know what's the suite number or what's the door number. So this is where sort of the port kind of comes in. So here now I'm going to give this a rate. I'm going to do, let's go with that number there, 50 milliseconds. And now I'm going to start Vehicle Spy. So if everything is working properly, I should hopefully be able to see a message here, symbol. Packet. And it's not transmitting. Why not? What did I do wrong? Oh, you know what? I know what I do. I was trying to answer the question for listen. I think I changed the number for transmit. I think that's what I did wrong. Yep. Okay, so I'm going to put this to 15. So you can see it proves the point that you can't transmit because it's not within the system bounds. Okay, so now I'm going to go in here, go back to my messages view. And hopefully this time it should give me something. Okay, I think I see something now. Pause. So here now I can see my message, and I notice my message because it's green. So whenever you're transmitting something from Vehicle Spy, you'll see a green dot. So we'll see the beacon, we'll see the sync or the commits, SSD, and again the packet. So here's my message. So if I expand it out, we see a message. Now, if you're used to working with CAN and LIN, you're kind of used to seeing this already. The only difference between the Ethernet frame and like other formats is that you'll see a lot more information here about the frame. So normally when you look at LIN, you have a message ID. If you look at CAN, you have a LIN, you have a message ID or an arbitration ID. Here, Ethernet doesn't technically have a message ID. It's really a combination of looking at the MAC addresses, the IP addresses, and the ports to know kind of what it is. And over time, it's just you'll learn these numbers. You're not going to learn them immediately, but over time, just like you did with CAN and LIN, you'll learn them. You'll just learn how to recognize them. So here we'll see, like, we can see the broadcast, and Vehicle Spy is smart enough to tell me it's broadcast because I did send all Fs. And then down here, I can see my message because I am awesome. And then we can see all the other information that's part of that. So here, what I can do now is I can go ahead and open up like Wireshark, for example. And here I'm going to open up and I'm going to connect specifically to my Meteor. So here, if I go into my Meteor, I should be able to see that exact message now. I'm going to stop it. And we can see the message that's being sent because I can see the raw data. And because I'm using text, it just decodes the ASCII. I don't need a database to decode that. However, I know you can do different plugins into this to be able to do some dissecting. In this case, I'm just trying to show you that you can use like the Meteor to do some media, use it as a media converter. Okay. Okay. And the last part I was going to show you, because I never taught this before, or at least a specific one, I've never shown anybody before. And I thought it'd be good to do something unique for this, is show you how to do burst mode. So burst mode, if I wanted to do burst mode for my PC, I actually cannot do that. The PC is actually too slow to be able to communicate that quickly. So here what I'm going to do is I'm actually going to get rid of this rate, and I'm actually going to create a function block. Function block is a way to script within Vehicle Spy. So here I click scripting automation, function blocks. I'm going to click plus to add a script. I'm going to stop Vehicle Spy temporarily. And here I'm going to do, I'm going to rename this to be burst mode, in case you ever want to try this. And then from here, what I'm going to do is I'm actually going to do a loop. I'm going to do a start loop. I'm going to do, let's do 15 messages. And then from here, what I'm going to do is I'm going to transmit the message that I just created. So I'm going to select my Juan's message, and I'm going to do end loop. I'm going to select all these here. I'm going to delete these. And then one more thing I'm going to do is I'm going to add a wait or delay of 10 seconds. I don't want this to just start going to just send messages over and over. I want it to be a little bit of wait and then send a burst of these messages. The other thing, because this is fast, or it needs to be fast, I need to change one thing that normally you don't need to change. Normally the automatic time position is perfectly fine. For this one, I do need to set it to microseconds. If you ever worked with Vehicle Spy and done programming, if you've never seen blue, and usually this is black. Whenever you see blue, it's because it's set to microseconds. So now this, I can actually program now into Vehicle Spy or to Core Mini to my device. Now, Core Mini is a way to run a script in our device. So most of our tools support Core Mini. Fire 2s, Red 2s, Fire 3s, our Comets also support Core Mini. And it's just a way to run either a script or a gateway. So here I'm just going to run a real simple script inside the device because it's faster than my computer. And then I'm going to set the start type to immediately embedded only. What this allows me to do is run this script just in the Core Mini. And if I connect Vehicle Spy, this will not run on my PC. So I want this specifically to run in Core Mini. So here what I'm going to do now is I'm going to go to Tools, Core Mini Console. And then from here, I'm going to just click Send. And this puts it into my device. So now I can go into my messages, and actually I can actually work with Core Mini and my PC at the same time. So if I did this correctly, which I know I didn't already, because I forgot to set enable burst mode in the device. Here now I need to go into mode 2. I'm going to allow 20 burst mode. This timer should be perfectly fine at 255. I know if I use less than 180, I think it doesn't work properly. So usually I just max it out 255. Right settings. So this enables my burst mode for my specific device. So you can see that a device can be allowed or disallowed. And now I can go into this. And hopefully I should be able to see this. So pause. Next. And that is not what I was hoping for. Thought I did this correctly. Maybe I didn't. Okay, let me just make sure. So 1000, 15, send up the message loop. That looks good. It is microseconds. That is running Core Mini. Did I just stop running Core Mini? No, it's still running Core Mini. Okay, let me just try this one more time. And of course, it works last night, but it doesn't work today. Just the way things are, aren't they? And now it doesn't want to work. Okay. So I may have lied to you. Okay. I have a feeling I have to close this out again. And we open it. Apologize. Tried this multiple times and it worked perfectly, and today, of course, it doesn't work. Okay, messages. Transmit. So I can get this done quickly here. Plus. Once. Message. Signal. Text. Message. Text. Something different, smaller, maybe. Shouldn't matter. And then TX panel. Oh, helps if I put IPv4. Okay, I already messed that up. Okay, so let's just change this to Ethernet type IPv4. Signal. Just need something real simple here. Okay, now in TX panel, it should be okay. I don't need to change anything. Function block. Okay, change this to start embedded only. Microseconds. Wait for. Start loop. Transmit. And loop. Delete. Okay. Try this again. Okay, that looks better. Okay, so symbol. Okay, so here's the burst mode. So we see the beacon and we see the beginning of the message. And of course, it gives me the node count. And then here you can start seeing where it starts to increment. So the first message would be 1, and then I can go down to the 15th. And then after that, the message goes out one more time, and then we can see the end of sequence for the burst mode. And then the system resumes again. And after that, it goes to beacon. So because I have it on the loop, this will go out every 10 seconds. So it'll do a burst. And so now we can use vehicle spy to see that. So from a presentation perspective, that's pretty much it. I just want to show you that we do have a lot more training classes available. So if you want to learn 10BASE-T1S, if you want to do the hands-on portion of it, you can certainly take this in our tour office. If you're not in Michigan, ping us. We can see what we can work out. We do have a lot of other options to take on. Some of these are offered just on site. Some of these are offered online as well. And then here I put the link to get you to where you can schedule, where you can look at the scheduling for the rest of the year. So again, don't be afraid to reach out. Just because we have things scheduled doesn't mean we don't do one-offs. So if your team requires this, just let us know. We can see what we can do. I do have additional resources available. So I usually, people always ask me about the creating an advanced graphical panel, so how to create your own graphics. I have a video on how to do that. If you're trying to do fault injection with CAN, I have an example online how to do that as well. So if you have if you need to do any of that. If you want to reach out to us, whether it's for questions what we covered today in the future, or you just have general questions, you can always do like ICS sales support. I mean ICS sales or ICS support. They will route it to the right person. In some cases, it'll be me. In some cases, it won't be me. But you will always get an answer. Other than that, if you have any additional questions, I will stick around. Otherwise, I am done. Yay!
Yay, good job, Juan. Yeah, just before we wrap up, we want to give people a couple more minutes to submit some last questions. I also sent out a poll, so if people can take a few minutes just to answer those questions. I also shared Intrepid's link tree as well as Juan's LinkedIn, as well as the link to our most recent, or I'm sorry, our upcoming class. It's funny, I said August 8th, it's August 13th. I'll change that. But there's a link for that for our next 10BASE-T1S hands-on training. So go ahead and take a look at all those. And feel free to finish up the poll. And Juan, there's a handful of questions coming in.
Yep, I see that.
That's all I have, so go ahead.
Okay, so one question is what database format is used for messages? So DBC would be one. The one that's really being used more right now is ARXML. ARXML. That's the newest one that's being used for AUTOSAR. Most of the industry seems to be moving to that. Occasionally, we still see DBCs with older architectures, but newer stuff tends to be ARXMLs. Another question: did you save your change to burst mode? Not sure I understand. I don't think I have enough context. I think I moved on too quickly after that. Let me see. Which RAD module would be the best option to use for vehicle diagnostics, data acquisition, or flashing mod programming? Which, with no intention of bench testing. David, depends on what that really means, because it depends on what networks you're using. So for that one, I would need to know a little bit more what networks you're using to be able to suggest. Because if you're just using CAN, I mean, Fire 2, Red 2, Fire 3 would be good options. But ultimately, it depends what networks you're working with, which one would make more sense. Let me see, 10 generic question about determinism. How the bus throughput can be split between ECUs. So for example, to have one ECU having guaranteed 60% of the total bus throughput, second having 30. So, okay, so one question is how do you control the throughput? I assume it's, yeah, 10BASE-T1S. You really, So there is one thing I didn't talk about. So I believe it's ADI who's going to be doing this, where it'll allow you to use more than one node ID. So you can potentially assign node 1, and maybe node 5, for example. So potentially you can have it given more throughput. I don't think you'd be able to get it that granular or that fine to be exactly 60% and 30% or 10%, but that would give you a few more opportunities to transmit. Another way to kind of mitigate some of that would be how long the messages are. So the longer the messages, obviously that takes up more time in a cycle. So that would be another one. So another question, is it possible to guarantee that a particular ECU will be able to transmit at least every X milliseconds? No, because the sequencing is no matter what, the sequence is a sequence. You can't go against what's meant to do. Another question is, what happens if you end up with two node IDs of the same one? So that one's what happens is one will probably start communicating before the other one. And so in that case, if that were to happen, one needs to stop talking. So the second one that doesn't start communicating will not talk. So it might be able to talk again in the second cycle. So you'll get some delays. So usually, if everything's configured correctly, that should never happen. The only time in theory you should ever see that is if your tool is misconfigured. So in that case, you need to make sure that you get rid of the module. But in that case, you're kind of fighting who's going to communicate first. So which RAD module for in-vehicle usage when we finally do see 10BASE-T1S technology? So that one at this very moment would be a Comet 2 or a Comet 3. It just depends if you need 2 channels or if you need 6 channels of 10BASE-T1S. I know we're going to have more tools in the future, but as of right now, it's just a RAD-Comets 2 and 3 at this very moment. And the Meteor, of course. So another question was, what case of normal operation and what case of failure of the coordinator? So failure could be loses power. I mean, that could be one. So like in a crash, it could lose power. If you're trying to lose loss of comm, you might pull power in a thing, or just something happens in the module, right? Sometimes they can burn out too. It doesn't happen very often, but it can happen. Usually it's more losing power than anything else. Okay, I think I answered all the questions. I don't see anything new. Is there a reason you don't connect to the last node with a single connection? Because you don't need to move. No, you can connect to the last node. It just depends if you can. So I'm assuming you're talking about, let me see. You're probably talking about this specific node. I mean, you would technically, well, here you wouldn't have a last, I mean, it would still be no matter what here. If I connect here, I would still be between these two nodes. If this happened to have a connector that pigtails, gives me pigtail, I could connect to that the same way and it'd be okay. But it's unlikely you'll have that. But it depends on the modules. I don't know what they'll do. You can daisy chain off wherever you can. It's not necessarily, you don't necessarily have to daisy chain off any specific location. As long as you have access to the wiring, you can daisy chain off of any location. So like in this case, in the picture I'm showing, if node 6 just doesn't have the pin up, you wouldn't be able to do that. So it depends on what is available.
Okay, we're about 15 minutes over, so I think we're gonna do last call. All right, I think we're good. Thank you so much again for joining us today. Feel free to reach out to Juan directly if you guys have any more questions. And yeah, I think that's it. Juan, anything else?
No, that's it. Thank you for joining.
Great. All right,
Good
have a great
afternoon.
day, everyone.